The number one reason developers quit Rust is the borrow checker. You write code that would compile perfectly in C++ or Python, and the compiler flat out rejects it. But it isn't broken, it's enforcing a strict mathematical model to guarantee memory safety without a garbage collector. To stop fighting the compiler, you have to start visualizing memory exactly the way it does. Which brings us to rule number one, ownership. In Rust, every piece of data has exactly one owner. Let's say we create an array to hold some state for our engine. The metadata, like the pointer, length, and capacity, goes here on the stack. The heavy data goes to the heap. Think of this pointer line as a pink slip. Right now the main function holds it, so the main function owns the memory. But watch what happens when we call a worker function. We didn't copy the array, we physically moved the ownership. The main function just handed the pink slip to the worker, and now the main function is completely empty. When that worker function finishes, its scope is destroyed, and since it owned the data, it takes that heap memory down with it. It's instantly cleaned up. So, if the main function tries to use that array again, the compiler blocks it. A bug that would cause a massive crash in C++ is caught right here in the terminal. But if ownership was the only rule, Rust would actually be a nightmare to use. You can't just permanently hand over your data every time a random function needs to read it. We need a way to let other code look at the memory without actually taking the pink slip. That's where borrowing comes in. By slapping an ampersand on it, we create a reference. We're basically telling the compiler, hey, I don't want to give this away, I just need a read-only view of it. Watch the new laser. It's purple for a reason. This is a reference tether. The main function still completely owns the data, but our logger function is now allowed to safely peek at those memory addresses in real time. And here's the best part. When the logger function finishes, the reference is destroyed, but the actual data is completely untouched. The main function never lost control. Nothing was moved and nothing crashed. Total memory safety with zero performance cost. That is the power of the borrow. Now, borrowing isn't just about reading. In a real-world engine, you eventually need to change the state, but it's exactly where Rust's most famous feature, the borrow checker, becomes your best friend. Rust has a golden rule. You can have as many readers as you want, or exactly one writer, but you can never ever have both at the same time. Watch what happens when we try to create a mutable reference while that reader is still active. If one part of your code changes data while another part is trying to read it, you get a data race. In other languages, this is a random, silent crash in production, but in Rust, it's a compile time error. The compiler sees the conflict and stops you before you even hit run. It's a literal guarantee of thread safety that makes your code rock solid. That is the true power of the borrow checker. So, how do we fix a data race? We don't necessarily have to change what we're doing, we just need to carefully control when we do it. And in Rust, we manage lifetimes using scopes. By wrapping our read-only borrow inside these curly brackets, we restrict its lifetime. The moment execution hits that closing bracket, the read-only reference is completely destroyed. Because the reader is officially gone, the borrow checker happily grants us exclusive mutable access. We safely overwrite the memory in the heap, and the compiler gives us the green light. Total memory safety and data race prevention, which is strictly enforced at compile time with zero runtime overhead. So, let's zoom out and summarize the 3 golden rules of Rust memory safety that we just proved. Rule 1. Every piece of data has exactly one owner, and when that owner goes out of scope, the memory is safely dropped. Rule 2. You can have as many read-only references as you want, as long as the data isn't changing. Rule 3. You can only have one mutable reference at a time, and it must be exclusive. By enforcing these rules at compile time, Rust gives you the speed of C++ without the fear of memory corruption. Alright, so that's the borrow checker. If you just stick to these 3 rules, memory safety is guaranteed at compile time. But there's a catch. Eventually, your architecture gets complicated. You start passing references across different structs, and the compiler can't automatically prove how long they're supposed to live. That's when you have to use explicit lifetimes. In the next video, we'll break down this exact syntax and show how to actually manually link lifespans so you can route data with zero overhead. I'll catch you in the next one.